In every single wire, from the one charging your phone to the guts of a supercomputer, there's a kind of paradox. See, we have two completely different but equally true ways of describing what the electricity inside is actually doing. One is simple, it's intuitive. The other, well, it's just plain weird. So today, we're going to unravel how both of these truths can exist at the exact same time. So let's just dive right into the central mystery here. If you ask a physicist, is an electron a tiny little particle, like a ball, or is it a spread out wave? They're going to look at you and say, yes. Now that sounds like a total contradiction, but it's not. This strange duality is actually the key to understanding, well, pretty much everything, from a simple light bulb all the way up to a quantum computer. So to really get our heads around this, we're going to look at two very different stories about the electrons flowing through a wire. One is the simple, familiar one we all kind of know. The other is strange, but incredibly powerful. And you need both of them. Okay, so this slide really lays it all out for us. On the one hand, you've got the classical view. It treats electrons like these tiny little balls flowing through a pipe. It's simple, it makes sense, and it's perfect for understanding big stuff, like the circuits in your house. But on the other hand, you have the quantum view. Here, the electron isn't a ball at all. It's a spread-out wave of probability. It's weird for sure, but it's absolutely necessary if you want to understand the microscopic world of modern electronics. All right, first up, let's talk about the version of electricity we all learn about in school. The one that keeps our lights on and our devices charged. In this classical world, things are pretty straightforward, right? We just imagine electrical current as a river of tiny electron particles. They're all just kind of drifting along in the same general direction, bumping into things, and carrying energy with them. It's a really easy-to-picture model of physical objects just moving. And look, it's super important to get this. This model isn't wrong, not at all. It's actually an incredibly powerful and useful tool. This is the standard toolkit for basically every electrical engineer. All those familiar rules, like Ohm's law, they're all based on this particle idea. For any big-scale job, like wiring a house or designing a city's power grid, this is all you'll ever need. But what happens when we zoom in? I mean, way, way in, down to the level of individual atoms inside that same wire? Yeah, this is where things get really weird and wavy. So down here in the quantum world, that whole tiny ball idea it vanishes. An electron is described by something called a wave function. Think of it like a weather map for an electron, showing all the places it's most likely to be at any given moment. So current isn't a flow of definite little particles anymore. It's the collective motion of these probability waves moving through the atomic structure of the metal.
And this is a huge point. The whole reason metals are such good conductors is because electrons act like waves. There's this idea called band theory, which basically says that inside a perfectly ordered metal crystal, these electron waves can just glide through the atoms with almost zero resistance. It's almost like a ghost passing right through a wall.
So what about resistance? Well, this completely flips the script on that too. It's not about little particles bumping into atoms anymore. Instead, resistance happens when something messes up that perfect atomic pattern, maybe an impurity, a defect, or even just the vibrations from heat. And that disturbance scatters those smoothly flowing electron waves. Okay, deep breath. We've got particles, and we've got waves. Two totally different stories. So, how in the world can they both be true? Let's build the bridge that connects these two worlds. This is it. This is the big question we've been building up to. How do you get that simple, predictable flow of particles from this bizarre, probabilistic world of waves? Well, the answer comes from the brilliant physicist Niels Bohr with something called the correspondence principle. Basically, what Bohr was saying is that quantum mechanics has a reality check built right into it. When you scale it up from just one or two particles to the trillions and trillions you'd find in a wire, its strange rules have to start looking like the familiar, classical results we see in our everyday world.
Okay, check this out. This table breaks down exactly how it all fits together. At the very top, you have the fundamental reality, individual electron waves, doing their weird quantum thing. But in a real wire, you have trillions of them. So when you look at their collective statistical behavior, that middle row, all that individual quantum weirdness just gets averaged out. And what comes out at the bottom? What emerges? The smooth, predictable flow that we measure and call classical current.
Here's maybe the best analogy for this whole thing.
Imagine a giant crowd leaving a stadium. If you try to track one single person, their path is going to be chaotic and totally unpredictable, right? They might stop, turn around, bump into someone. That's your quantum electron. But if you zoom out and look at the entire crowd from above, you see a smooth, predictable flow moving toward the exits. That's our classical current.
So what's the big takeaway here? It's that these aren't competing theories. They're descriptions for different scales. And knowing which one to use is exactly what makes all of our modern technology possible. And this slide really brings it all home. It's about using the right tool for the job. If you're an electrician wiring a house, you're thinking in classical terms. Particles, current, voltage, simple. But if you're an engineer designing a computer chip where the parts are just a few atoms wide, you absolutely must think in quantum terms of waves and probabilities. Different scales demand different toolkits.
I mean, seriously, this quantum view isn't just theory. It has literally built our entire modern world. Every single transistor in your phone and computer relies on it. Flash memory works because of a truly bizarre effect called quantum tunneling, where electron waves can literally pass through solid barriers. Superconductors, MRIs, none of this would even exist if we didn't understand the electron as a wave.
So, if you take just one thing away from this explainer today, let it be this. The simple, solid, classical world we all see and measure is really just the large-scale shadow of a much deeper, weirder, and honestly more wonderful quantum reality. One doesn't replace the other. The classical simply emerges from the quantum. And that really just leaves us with a final thought to ponder. The flow of electricity is just one example of this. What other things that seem simple and solid in our everyday lives are actually the result of countless complex interactions happening just beneath the surface, completely hidden from view? Thanks for watching.